Alright, so before we start with the actual material, just a couple quick announcements. There wasn't really a unanimous choice on the best day and time for a review session next week, so I just went with the majority. And the most people said they were able to make it to one immediately after class next Wednesday, so at 11 o'clock till about 12:30. That'll be in the Rosenblatt room.
We have class at 12.
You have class at 12? Alright, so from 11 to 12. The idea is it's not going to be like, I'm not bringing slides and a talk. You bring questions. It'll be a more of a Q&A type review for us to touch on topics that you want some extra focus on. The couple of you that need to reschedule taking the midterm, stick around and let's chat after lecture. So, and my grader has kind of gone AWOL, so I need to track down the homework still. I promise I'll try to get this. I'll try to get. You will have all of the homeworks by Wednesday. That's guaranteed. Your homework to me. So. Alright, so on Wednesday we finished up with, or when we finished we had just gone through a hurried derivation of the material derivative. And since the material derivative is so important, we're going to go ahead and take the time to go through that derivation one more time in a slightly different form. Just kind of touch on that again. So recall that we can have some, some field representation of a variable. We'll say, we'll call this variable b, right? And b can be a scalar, a vector, you name it, density, velocity, doesn't matter, right? It's just b. And the idea is that then we can say b is equal to b of x, y, z, and t, right? And so if we want to take the derivative of b with respect to time, we have to apply the chain rule. So the way we did so was that b dt is equal to b t plus b partial x partial t plus b partial y plus partial b partial z partial z partial t. Right. The idea here being that the x, y, and z components of a particle, right? If we're saying that, so we're following some particle A, right? And tracking the rate of change of this quantity b, of this property b, on this particle A, then we write it like so. Because x, y, and z of A correspond to the position of this particle, so they themselves are functions of time. And so this is simply a chain rule expansion where we have the partial with respect to time itself, partial with respect to x with respect to time, so that the x's cancel, we end up with dv dt, y's cancel, z's cancel, and it's just a long expression of basic calculus here. And the idea was that because x, y, and z describe the position of the particle in time, right? If we say that xa is equal to, as the vector form is equal to x a I plus y a j plus z a k, then the then that means that the time derivative of this is equal to dxa dt I plus dya dt j plus dza dt k, or equal to the velocity of a, right? The time derivative of x is equal to velocity, so we end up with u I plus vj plus wk. And so if we look at this, we see that we have terms, specifically these ones here, with which we can make a substitution for the velocities. Yeah? And so we end up with is saying, all right, well, we've got now dBA dt is equal to, well, it's the total rate of change, I should say. dBA dt is equal to partial b partial t plus u dBA dx plus v a dx, or dy plus w dBA dz. And so this is essentially what we call the material derivative, but we took it one step further and went ahead and wrote this as equal partial BA partial t plus the velocity vector dotted with the gradient operator of b. Usually we put this in parentheses. And then on the left-hand side, we went ahead and changed notation a little bit and called this dBA capital D. So this is the focus of today's lecture, the material derivative. And what we didn't quite get into on Wednesday was what this means, the interpretation so much. So if we kind of follow the chain of logic through here, we know that a particle that we've called A, right, is traveling through space, and we have this this field representation of space that says we know the value of B, you know, everywhere in our domain. So you know, whether it's temperature or velocity, we have either a velocity field or we have a temperature map, you name it. And so as this particle travels through the field, we have some component of its rate of change that is equal to the rate of change at a given location in the field. So this is our unsteady effect. This is what's called our local derivative. This is telling us that at the position of A, the value in the field itself is changing in time. So this comes from our unsteadiness of the variable B in space. And then at the same time, we have this component, which we call the convective derivative. And the reason it's called that is because we have here the rate of change in space times the speed at which it's traveling through space, and the product of those two work out to give us a time derivative of B. So the idea being, if we come up with an analog here, let's say we've got a ramp at some angle theta. We've got a motorcyclist riding up this ramp. Right? The idea is we're going to make B here equal to the height of his axles off the ground. Okay. Let me find my example here, because it's written. All right. And our coordinate system is like so, x, y. So, as I said, B here is the height of the axles off the ground, and we can go ahead and write or draw the case where he's actually on the ramp now. I don't know which, let's pick an axle. Let's say it's the front one. Okay. So at this point, his velocity in space. Well, first of all, if we look at this system, if he's riding up the ramp at some steady velocity, right? If u is not changing in time, is there any local derivative? Is there anything about the system that is changing in time? No. No earthquakes, this ramp isn't heaving up and down, it's staying fixed. It's being a good solid, not moving. So our, let me write it one more time here, dh dt is equal to partial h partial t times u so that means this component goes to 0, all right? What about, okay, you guys know that, especially when this is a scalar, this can be rewritten as u dot grad h, right? These two statements are equivalent. So what is grad h here in terms of our x, y coordinates? Well, h at a point is simply equal to the elevation off the ground, right? So if we were to write h as a field, h, x, y, z, t, this is simply going to be equal to, well, what's its dependence on the x direction? Let's go with Matt. What do you think? What do you think we put in for h? How do you think we write h in terms of x, y, z, t? Huh?
H would increase as the side of x.
If you were to pick any region in space, if I were to say, here's a point, what is h equal to?
Difference between that and x-axis.
So you measure that's just y, right? It's
right.
the value of y there. So its field representation is simply equal to y. Yeah? Which means that if we go ahead and keep the wrong, I have some wrong markers. So we have h, x, y, z, t is equal to y. All right, so grad h, what is this going to be equal to? Let's go with Caleb.
It must be the sine of theta times
Well, I mean, if this is our function, right? What's grad y? Remember, it's going to be a vector. So the gradient of something is equal to its partial with respect to x times I plus partial with respect to y times j plus, so on and so forth. Is there any dependence on x? ddx of y equal to 0, right? 0. How about with respect to y? What's partial y with respect to y? 1, right? Just just equal to 1. And of course there's no z, there's no t, and so everything else goes to 0, which means that grad h is just equal to 0I plus 1j. And since this is a 2D problem, let's go ahead and leave z out of it. Alright, now his velocity when he's on the ramp in our xy coordinates. We're assuming that he's riding straight up the ramp. Right, so this is also going to be a vector. And who wants to volunteer a velocity vector? Let's say the magnitude of his velocity is u0. Okay. So the scalar, let's say he's going 100 miles an hour. It's brave. 3 miles an hour is me. Joey.
W v naught cosine theta I plus v naught sine theta j.
Yes. All right, so we have in this box everything we need to compute the time rate of change of this point, this axle, there we go. The time rate of change of this axle, height above the ground, as a function of what our field variables. No, look at what we used to get this. We looked at the ramp, and we looked at how the velocity of this particle traveling up the ramp. This could be because we shoot a radar gun right here, right? We can essentially say that as he's passing this point, we know how fast he's going. We don't have to track the actual bike itself. We just need to know how fast the velocity, or what the velocity is at this point in space. And we also know the characteristics of the ramp as functions of space, or as a function of space. So we can be completely blind as to what he's doing before and after he goes through this point. So we have observed him in an Eulerian frame of reference. We've seen it. We're seeing him as he goes by this spot. But by using the information we've collected about that spot, we can now derive the Lagrangian rate of change. And let's go ahead and do that. If we plug things in here, our velocity vector times grad h is going to be equal to what? Well, it's just a dot product, right? We've got our vectors here. So 0 times u cosine theta, it's not very exciting. 1 times u sine theta, and being just 1 times u naught sine theta, and that's it. So we can say now dh axle dt is equal to, because we showed that nothing about the system itself is changing at this point in space, we just have u naught sine theta. Does this make sense? I hope so. He's traveling up the ramp, the given speed, we know the shape of the ramp. He's going to be moving vertically with a velocity component that is the sine of his total velocity. But the subtle thing here, and I really want to drive this home, is that all we did was we took a snapshot of what was happening at this point in space at the time that he's traveling through it. So Eulerian frame of reference, field representation, we end up getting a Lagrangian rate of change. So this is the real value in the material derivative, because this allows us to take information about the field, stuff we have measured from a stationary frame, and infer things about particles that are moving through the field. without having to observe them directly. So this is the tool we use to tie the two things together. Okay. So anyway, so for the rest of this, we're just going to be, that was most of our review of the material derivative, and we're going to start getting into what control volumes are and their relationships to systems of fluids and how we apply the material derivative to them. And we'll get into the motivation for the Reynolds transport theorem, but because this was designed to be an hour-and-a-half lecture originally and we're one behind still, we probably won't get to that today. So, as I said, the value, Lagrangian rate of change is equal to the Eulerian rate of change at a point, at the point where we're observing stuff, plus the convective rate of change of the particle's motion through the field. So as another example, let's consider a case where we've got like temperature measured in a room, right? We've got 3 points. That this is supposed to be degree signs. Point A is at 100 degrees, point C is at 50 degrees, point B is at 0 degrees. And let's go ahead and say, well, now at a fixed point, any one of these points, the rate of change, is just equal to partial t at point. So that's our Eulerian time derivative. This tells us about the steadiness of the field. Now, let's imagine that there's a fly flying through this room that we've got here on the slide. It starts out at point A, and it's heading over to point B. So the Lagrangian time derivative, that is the rate of change of temperature of the fly as it travels, not only includes the unsteadiness of the temperature in the room, but also the apparent unsteadiness, that is the temperature changes that the fly sees because of its own motion, that being the convective term. So from point A to point C, it's gone from 100 degrees to 0 degrees. Even if the room has stayed at a steady temperature during that time, the fly has changed. And so the way we write this, just as we did with the ramp case, is the rate of change of the temperature of the fly is equal to the unsteadiness in the room plus the rate through which it travels through a spatially changing temperature field. So, if you remember when we were talking about, I think it was in pressure fields as such, and in chapter 1 as well, the book said that incompressible flow, the definition of incompressible flow was one where the density is constant. That's actually not correct, right? The true definition of incompressible flow is that the material derivative of the density is equal to 0. What this means is that the density of each fluid particle remains constant, not necessarily that the density of the fluid is the same everywhere. Right, you could have, for example, a mixture of, let's say you've thrown a bunch of rocks into a fast-moving river and they're getting dragged along by the water. Is anything in this system compressible? No. You got rocks, you got water. But is the density constant in the field either? No. Because it's not a homogeneous mixture. So if you have a constant density, that means that it's the same fluid. It's a homogeneous, incompressible case. But the more general statement is to say that the density of each point, or each particle of material that you have in your system doesn't change in time. These started out as PowerPoint from Mac, and so it keeps throwing in 1/2s instead of rows. So again, be mindful of this difference. It doesn't mean that the spatial variation in density is 0, and it doesn't mean that the time variation in density is 0. It just means that each particle itself constant density. All right, let's look at a water heater. This is another good example where you encounter in everyday life where you have a steady system, right? You can be taking a shower, and nothing in here is changing in time, but you have a cold inlet and a hot outlet. And the way the rate of change of temperature occurs is because if it's hot here, it's cold here, and water is traveling from here to here, it has to heat up somehow. And if nothing in here, if the temperature at this point is, rate of change in this point in time is 0, then the only way it does that is by traveling through a spatially changing temperature field. Yeah. Okay. So, let's do another example here. So what we've got here is a sort of a converging nozzle, or just a narrowing pipe with an inlet velocity of 0.5 t meters per second, outlet velocity of 1 t meters per second, or t is in seconds. Okay, so step 1 is we're going to try to determine the local accelerations at points 1 and 2, and then figure out what the average convective acceleration is between points 1 and 2, because these are the two components that make up the material derivative. So, okay. And we're talking about the Alright, so local acceleration, which term am I interested in? Perfection. I heard two different answers. The first one, that's correct, yes. Local because, remember, this is telling us how, if we pick a space and time, for example, at point 1, we're interested in what is the acceleration at point 1 without worrying about, following an individual fluid particle. So if we say that time rate of change of velocity at 1, right? Velocity 1 is equal to 0.5 t meters per second. So the time rate of change of this is going to be 0.5 meters per second squared. Yeah? No, this doesn't tell us anything about the rate of the local acceleration here, 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 or here. It's just only at point 1 at the inlet there. V2 is equal to 1.0 t meters per second, and so its local rate of change is equal to 1 meter per second squared. Okay, what about the convective term? How would we go about, this is a fairly easy one to sort of intuit what the convective term is going to look like. But we don't have the specific information to solve for it exactly. But what do we know about conservation of mass? If we've got inlet, outlet of different sizes, what was one of the governing equations that we used to constrain the problem? Right. Rate in equals rate out. Yeah? Conservation of mass, incompressible fluid like this. It's homogeneous, it means conservation of volume. So we've got V1 A1 is equal to V2 A2. Just looking at this, is V2 or is A2 A1? Which one's larger? No, if you're talking about cross-sectional areas. A1's larger, which means that V2 is going to be larger. Yeah. So. One's larger. So we've got that V2 minus V1 is greater than 0, right? Okay. This is really kind of a one-dimensional problem, right? We're not like we can look at this and see that the gradient is only going to give us a rate of change in the x direction, because it's a 2D problem and it's symmetric. So this tells us that grad v is going to be equal to d dx v I plus 0j plus 0k. V2 minus V1 can be written as the integral from x1 to x2 of dv dx, which is equal to an average dv dx times x1 minus x2 minus x1. This makes sense, you know. We're just integrating the rate of change of the velocity with x between the 2 points. This is all symbolic. We don't have any numbers to actually plug in here. But the idea is we can carry x2 minus x1 because we have this equivalency where we can say now that v2 minus v1 divided by x2 minus x1 is equal to the average rate of change with x. And if we look here, this is essentially our convective acceleration term, right? The average convective acceleration. Average convective acceleration between points 1 and 2. We already showed that v2 is larger than v1, right? v2 minus v1 is greater than 0. x2 minus x1, just by looking at this, is greater than 0, so this is positive. So our average convective acceleration must also be positive. Does this make sense? If a point starts out here, and it's going this way, it's speeding up or slowing down. If a particle, fluid particle, we throw a little probe in here and monitor its velocity as it moves down the pipe. It's going to be speeding up, right? So its apparent rate of change is going to be greater than 1, or greater than 0. So, positive. Okay. Let's talk about fish. I guess before we move on, does this make sense? Are there any lingering questions about this and the stuff we've done leading up to it? Any points for clarification? No. Okay. So, example 2. Let's consider a river. We know the velocity field in terms of x, y, z, t. And we have somehow measured the concentration of dissolved oxygen in the water. Right, this is given as a function of x, y, z, t. So we have v, we have f, both as field variables. Yeah, Eulerian frame. A fish in the river has an absolute velocity of u as a function of t. Okay, so we know the velocity of the fish based on where it is in space, because it has, or yeah. So let me. So, first question. How would we express the time rate of change of the dissolved oxygen concentration as experienced by the fish? Let's get Eric. Part A, you want to take a whack at?
So material derivative with function f of x, y, t, z, t, and then
So we've got two terms in the material derivative, right? The local and the convective. So let's just start with local. Do we know anything about whether the oxygen concentration is steady or not? Is any information about that given? Are there any assumptions to be made? No.
assume it's steady.
We can't assume it's steady. So we will have a df, a partial f, partial t term for now. If someone later tells us it's steady, that'll go to 0. Plus, well, we know we're going to have, we're going to have, well, let's let you work on the convective term. We know we have a velocity, a gradient, and an f. Yeah, so we're going to have an f, but what do you think we use for the velocity here?
Philosophy.
Huh? U of t. Yeah. Why doesn't the velocity field of the river come into play? We have velocity of the fish. We have velocity of the river. What is? Why aren't we concerned with accounting for the river's flow?
Ask for the fish.
That's for fish. Yeah.
By fish.
Exactly. And because we have f as a function of space, the flow field has nothing to do with it. Right? It's just the red herring, so to speak. All right. So A. Good. So we got B. Let's say the fish lays eggs that drift along with the flow. Now, what is the rate of change of the dissolved oxygen as experienced by the eggs? Let's go with Jackson.
It's Eulerian, so
Is anything going to change about our assumption about the steadiness?
no.
Okay, so we have t plus, we have eggs drifting along with the current of the river. So what's their velocity?
The velocity just be 0. It's going to be the same as the water.
Same as the water, exactly. So instead of a velocity of u, it's going to have a velocity of v. Right? So it's being convected through this field of f with some velocity v, which is the river velocity. So now instead of u, we just have, right? And part C, some of the eggs eventually, get themselves stuck in the mud or under a rock or something and stay there. So the rate of change of dissolved oxygen is experienced by those eggs that are stuck. Andrew.
It'll be just the df/dt term goes to 0, right?
Think that this term's going to go to 0? Well, why would this?
Oh, wait, no.
So we still don't know anything about the rate of change, right?
The
So
local is still there. So the velocity of the egg goes to 0, which is the velocity field. So that just 0.
0 here. Good. Yep. So Just bear in mind that we have to use the correct velocity, for the particles that we're interested in tracking, and that our field representation is a field representation because it's fixed in space. It's the Eulerian reference. So this example was kind of designed to confuse the issue a little bit and try to demonstrate how it's easy to mix up the Eulerian and Lagrangian, representations here. So again, we're back to this. I know you're probably sick of Euler and Lagrange, but just always remember Lagrangian. This time we're going to call it a systems approach. Can describe not only a given particle, but may also define a collection of particles as what we call a system, a defined mass or collection of matter as it moves around and possibly interacts with other things. Okay, I think on day one I said that conservation of mass of a fluid is equal to says that the rate of change of mass in a material volume or a system is equal to 0. And essentially that was a expression of the material derivative being equal to 0, which says that, for example, if you put a pot of water on the stove, the system, or the Lagrangian approach, means tracking all of the molecules that are in that pot of water. If it boils, well, you track the molecules as they boil off and turn into vapor, but if you take that entire vapor cloud and all the liquid water that's left over, the mass in there does not change. They've just moved around, they've interacted, they've changed states and phases, etc. Whereas the Eulerian would be looking at a spot in the pot and saying, well, this is hotter than it was, or the density at this point has changed because all the water boiled off. So, system, collection of matter, a fixed identity, meaning always the same little pieces of matter, which may move, flow, and interact with the surroundings. A control volume, on the other hand, is what we call, it's a fixed volume in space. So this is sort of our Eulerian idea, right, of a collection of particles. If we had the Lagrangian idea of a fixed particle, and now moving to multiple particles, that's a system, then the Eulerian representation of point in space, we turn that into a higher dimensionality, we now have a volume in space, which we call a control volume. And a control surface, we define as the surfaces making up the control volume, right? If you've got a cubic control volume, it's just a cube in space, then the sides of that cube, all of the flat planar surfaces, make up your control surfaces. So if we think of something like Mount St. Helens, right, which is a little before your time, but back in my homeland in 1980, this really great, cool, majestic mountain just decided to blow itself up. And I don't know if you've ever seen the before and after pictures, but it's like, really iconic looking mountain, then afterwards it's just decimated, right? It wiped out a huge surrounding area by spewing ash, rocks, and lava all over the place. Really ruined everyone's day. So in this picture, let's say, what would we, if we were interested in tracking, what used to be the top of the mountain, what would be our system in all this? If we were to, well, we might say that it's the rock making up the mountain itself and all this billowing ash and stuff, right? Everything that was once contained inside of the mountain before it went volcano. Whereas we could say that a control volume is this box, imaginary box sitting on top of the mountain. So the difference here is that the system, it can do whatever it wants. The control volume has to stay fixed, and so the particles in a system can flow in and out of a control volume. Yeah? And they do so by flowing across the surfaces of the control volume, which are appropriately named the control surfaces. So, here's the problem. All of our nice laws of physics, things like F equals ma, conservation of mass, so on and so forth, are all written for a Lagrangian frame of reference. Think back to any like physics classes you've taken. If you're dealing with a trajectory on a baseball, if you're dealing with statics, it all has to do with loads, forces, responses of individual particles. You've never had to deal with when you have too many particles to actually keep track of. So we need to figure out a way to make these physics still hold, to be able to use these governing equations of motion and conservation equations in an Eulerian sense. That is, instead of having to apply F equals ma to every single particle in this ash cloud, we could see we were going to figure out a way to apply F equals ma to this control volume and figure out just how much upward thrust was created by, or downward thrust was created by the mountain launching all the particles into the air. So let's look at another example here. Conservation of mass. We've got a fire extinguisher. The system could be thought of as all of the matter that is contained inside of the tank. Yeah? The control surface would be the boundary of the tank, and the control volume would be the inside of the tank itself. So at time 0, before you open the valve, the control volume and the system are coincident. They're the same thing. However, once you open the valve and start letting all the gas out, or all the foam or firefighting agent out of the tank, some of the system has lost the control volume, so they no longer contain the same matter. However, if you kept track of this whole cloud, along with everything left in the tank, you'd see that the mass didn't change. You haven't gone Einstein on it and destroyed matter or created matter. The mass is the same, but that does not mean that the mass contained inside the control volume itself is unchanged. In fact, it has changed. We just see we lost, this whole cloud, whatever the mass of this is no longer contained inside the control volume. And so conservation of mass applies to systems, but not to the Eulerian idea of a control volume. So let's consider a couple more examples. Let's say we have what we call a fixed control volume. This could be if we take a section of pipe and we want to let's look at all the fluid that flows through this section of pipe. So if this black outline here is the pipe, we may have a control volume that we have defined as volume in this pipe with the control surfaces shown by the dashed blue lines here. And it stays fixed in space, so the rate of change of fluid going through the pipe simply dictates the rate of change of stuff going through the control volume. However, control volumes don't actually have to stay fixed. In fact, you're going to be doing this in the lab that's in November down at the MHL. But if you have something like a jet pump or a jet engine, it's moving through space too. We know how fast it's moving through space. We can usually draw a coordinate system in which it's not moving, but relative to the surroundings, it is moving. And so we have, at some point, we could say a system is made up of all of the particles that are inside of the jet engine at some point in time. But a few seconds later, all of those particles are going to be kicked back out into the exhaust. So your system starts out here, ends up here, your control volume moves on past. Another example of a moving and this time also deforming control volume is that of a balloon. Yeah? So you blow up a balloon, you let it go. The rate of change of mass of inside the balloon is obviously going to be less than 1. You're losing air out of the balloon is shrinking. And because of this expulsion of mass, we're going to see in the next lecture that we can actually calculate things like the thrust generated by this balloon gone berserk. So I think that's an okay introduction to systems and control volumes. We'll pick up with what we call the Reynolds transport theorem, which is applying material derivatives to this on Monday.
Do I use the word quiz?
I have those notebooks. No, my aunt gave me word today, and I was like, see,
I never know what you
in class.
Is the
I
Pretty
don't
good
know
shot.
where my aunt is.
Good or just fucking
Yeah, and why use the word quiz? Never
What is that?
Reorder.
Stop that, man. Oh, yeah.
That's yesterday.
Oh.
Sorry.
So it's just Jax and Sam, you guys were the
Yes,
only
sir.
two that needed to, alright. So, do you guys prefer doing it on Thursday or on following Monday?
I leave on Thursday.
You leave on
Early-
Thursday.
Early
Pretty early
Thursday, so I
Thursday.
can't do Thursday.
You guys have any objections to this on Monday?
No, I just would much rather, get the review
Yeah.
session.
Yes.
That's why I didn't wanna do it on Wednesday if the review
Yeah.
session was Wednesday.
Yeah, right. I want to give you guys a chance to do the review session before.
As long as you're okay with us doing Monday.
Yeah.
Would it be that afternoon or evening?
Yeah, it depends kind of on your guys' schedule. So my Mondays, I mean, this is my only fixed thing. Right? The rest of the day, I'm just banging my head against the thesis.
Evening would be ideal. I finish the classes at 4.
At 4?
Yes.
And
I finish it too, but
you finish it too?
I can do whatever is best.
Okay. So why don't we go ahead and say from say at 4:30. Does that work?
Yes, sir.
Are you on Central or?
Yeah, I'm in Central, but I'll drive up.
Okay. I mean, it's it's not going to be like weird or situation. So
That'd be awesome.
and I'll get the like the conference room or something for you guys to
Thank you so
sit
much.
down and yeah, no problem.
Appreciate it. Good weekend.
Yep, you too.